Okay, welcome everybody to the second video in our long series of remote classes. I would like to start off by saying I apologize that the last video was over an hour long. I promise that that will not be a common occurrence. I am going to time myself and do 50-minute lectures, essentially starting from the moment that I start these lectures and everything like that, so you will not have to bear with over an hour videos in the future. So we basically left off, we had talked about networking numbers, like the numbers that we see in networks on the internet, and we're talking millions and billions of people and devices, and we want to scale, and so far we've talked about a generic set of problems that we're going to face, and we obviously have not covered any solutions to any of those yet, but that's one of the big things we're going to do in this course. And so we're going to continue our introduction. So the next 50 minutes are basically just introducing you to network concepts, and it's going to introduce you to a lot of terminology, and I'm just going to kind of give you some examples of things that we'll be looking at, and that will kind of help us go from there. So in coming back to the material, so when we're talking about applications that must work across platforms, like I have a Mac and I want to have a network connection to a Windows server or a Linux server, etc., etc. We need some commonality between those two machines, a common way to represent things, the bits, and so ASCII or UTF-8, and then we need to talk about like who contacts whom and when, and all of that kind of stuff. And so we kind of have to start defining the exact rules for what must happen to do X, Y, and Z. And so that is basically a protocol. A protocol is just a set of steps necessary, like the example I used before. Whenever you're needing to ask somebody what time it is, you don't just walk up to them and give them a big old hug and a big wet kiss on the mouth saying, "Hey, what time is it?" That's not going to work. You're not going to get the time. If anything, you're going to get a punch in the face. There's a protocol. There's a greeting. Hello, I'm a human being. How are you doing? And then you move forward from there and eventually get to asking what the time is. And so we as humans have protocols for everything. A lot of the times we call them manners or something like that. But protocols for computers, it's about the same thing. It's just a set of steps that you need to do to get done what you want to do. And so there are lots of protocols at every layer, and so at the application level, our protocols are going to deal with names to addresses. That's one big thing. And then there are different protocols for different applications. For instance, one of the big protocols that we're going to look at is HTTP, Hypertext Transfer Protocol. And this is basically how we communicate web pages from one machine to another. As you know, there are many different kinds of browsers. There's Firefox, there's Chrome, there's Internet Explorer, there's Safari on the Mac, and that's just to name a few. So there are lots of applications that display web page content. And so HTTP is the protocol. We format the message just so that when you get it, you know exactly what to do with each piece, and thus we've defined a protocol. One of the protocols we'll be looking at that's very important, it's very prevalent on the internet, is TCP, which just stands for Transmission Control Protocol. We're going to talk much more about that when we talk about socket programming, which is going to be coming up in the next few days, as a matter of fact. But just to kind of give you an idea of what it means to define a protocol at this level, essentially whenever you are requesting a web page, there are about, at minimum, we'll say, 17 messages that get passed from your machine to some server in order to request one piece of one web page. It actually can be far more than 17, depending on how many images there are on the page, how many blocks of text, how many different pieces there are. But there's at least 17, okay? And the first 6 are messages, and again, it could even be more than 6 just for this process, but there is a set of messages that get passed around requesting, hey, I have a URL here, like google.com, what is the IP address? I need to know the IP address, the identifier for this particular machine. And so there are 6 messages just used for DNS translation from URL to IP messages, IP addresses. And then there are at least 3 messages that are sent back and forth just to set up a connection. And it's not like a physical connection, it's a logical connection. We'll get into that again when we talk about TCP. And then finally, after you've found the machine and after you've connected to the machine, and I put connected in quotes, now there are a number of messages for requesting the web page. You send a request and you get a reply, and then there's acknowledgments being passed back and forth, and then that's for one piece of a web page. You repeat this step for as many pieces as there are in the current web page, and not to mention any preloading type content. And then once that's done, there's 4 messages for tearing down or stopping that particular connection that we created in a previous thing. And by the way, I want you to, normally I ask this and ask for responses, but I typically love to ask the question, how many machines do you think are touched whenever you send one Google request? Like, I want to search for, this music video by this band, being very generic there. How many machines do you suppose actually get touched? In other words, see the request that you send out. I want you to get a guess in your head, and then I want you to double it, triple it, even more. We're talking anywhere from 2,000 to 20,000 machines are touched by your one query to Google. It depends, but on average I think it comes to about 20,000 machines that give a small piece of the whole response. And so this is a highly distributed process, and so networking is kind of what allows us to do this at such a scale. So the next time you do a Google search, I want you to think about just how many machines are working together to give you the response that you're requesting. It's pretty insane, actually. Okay, so that's kind of a notion, shall we say, of an application protocol. So whenever we're talking about this kind of stuff, there are different perspectives that we can look. And the perspective we're going to be taking more often in this class than anything is the perspective of the application programmer. Okay? And basically the programmer says, okay, well, this is what I need from the network. Here's a list of exact services that I need to utilize to do what I want to do. And there can be other requirements like, if you're talking about a real-time video chat, you're going to have some delay requirements. Like, it's not going to work if you say something and it takes 10 seconds for it to get there. Human beings don't communicate with that kind of a delay. It turns out to be very, very difficult to communicate. You keep interrupting each other whenever you say something and it doesn't get there for 7 seconds. So you really need, for applications like that, to be able to specify, I need at least this much network capacity and this much speed for this application to even work, right? Video streaming, you would hope that your ability to download the video is at least as fast as, you know, this many frames per second. You want to be able to download enough frames to be able to display them without having to wait and buffer and all that kind of stuff. So when we talk about all the application requirements, that's where we're going to be focusing in this class. But there are other perspectives. You have your network designer, and basically they're the ones who say, okay, well, we need this many devices, we need this many routers and switches in order to make, you know, these little local area networks, and here's how we're going to put them together. And so designing a network, that's actually a very complicated process, and that's something you would kind of learn more in a technology, like a hardware type focus on networking. Again, we're focused on the software side of things, we're focused on the applications, but that's all well and good, but if you don't have a well-designed network, you know, most of those requirements just kind of fly out the window. So a network designer, typically they make a lot of money because their job is very hard, and I'm hoping that we can get some information from some of the people that maintain and work on the Rose-Hulman network itself, and so we can kind of, you know, maybe get information like how many routers there are, about how much traffic is there in a given day, and all that kind of good stuff. Maybe, we'll see. And then lastly, you have the network provider. These are the people that are charging you for the use of their, you know, their networking services, like an ISP, or, you know, you have Google offers email servers for free, but, you know, you can pay for certain things and things like that. But a network provider is going to look very much at managing the network. If something crashes, how easy is it to interchange these things? And that's a perspective that's very important. But again, in this course, we're going to kind of try to look at all of these different elements. But again, we're going to be focused here at the application level. Okay, so some terms that are going to come up. All right, so when we're talking about connectivity, two machines being physically connected to one another, whether it's a point-to-point or we have multiple access, okay? A point-to-point is kind of the view when we're talking about one machine connected to another. To the application, we want it to look like this, where you just have a direct connection to that device. But there could actually be many, many routers between you and that device, but we want to hide that fact and make it appear as though you're directly connected. And then we have something like this, a multiple access. This is going to be your Ethernet-like networks, and Ethernet has adapted and evolved over the years. When it was first created, as I mentioned before, there was just one wire that would run through the entire building for an Ethernet, and then people would use these alligator clips that would cut into the rubber and make contact with the copper cable inside, and then you would plug the other end into your network card, and everybody was physically connected to this one line. And so if somebody sent out a message, it would just go to every other computer. And that's how the first Ethernets were designed. And there were a lot of requirements that came out of that, where it could only be 2,500 meters or less because of the way the protocols work. We're going to talk about that when we get into chapters 2 and 3. But the ability to share the resources is a very important ability to be able to do. You know, when you're dealing with a home network, you probably have something like Wi-Fi, and on a wireless type of a viewpoint, it still looks something like this, only the connections are using things like radio waves and things similar to that. And so the physics of that we won't really talk about in this class. That's for some other course. But we still have to worry about multiple machines on the same network. What happens if you have more than one machine wanting to say something at the same time? How do you share that medium? And that's a very big thing that we're going to talk about in chapters 2 and 3. And so some of the following terminology is really important. Okay, so scale. This first one, that is a word I've already used a lot, and that just speaks of how many machines or how many users can we add to the system and it still work? Like, how well does this scale? And so you want applications that scale very well for the number of users that are using the system. And so you might need this many servers for this many users, and you need to be able to grow to this many servers for this many users. And so you kind of need to know, like, what are my ranges of users that I can support, and how much is that going to cost me, and things like that. And so when we talk about a link, okay, when we say that two machines share a link is just some means of the connection, whether it's a cable, like a coaxial cable, copper cable, fiber optic, or a wireless link where you're dealing with not a physical wire, but you're using waves of some sort to have a link. And so we say that two machines, we speak of a link between them, and that's just some connection using some kind of medium. And then in the networking world, when we talk about end machines, we usually use the term node. So a node would be your computer. A node in the system would be a server or a phone. Just any of the systems that are connected to the network, we call them nodes. Okay, and so point-to-point is more of a logical kind of thing. In practice, we don't. It's very rare that you have two machines that are literally physically connected to one another, unless you have a point-to-point link from your machine, and this is, say, a router. That is more of what we have today. So point-to-point links do exist. They exist all over the place. Every time you connect to a Wi-Fi, that is a point-to-point link. Every time you connect to an Ethernet, that is a point-to-point link. But essentially, when you look at the network as a whole, you start talking about multiple access links, where with Wi-Fi you have more than one machine linking to the same device. And so that's things that we're going to talk about. And so when we talk about a switched network, what we're talking about is we're wanting to share the medium, right? There is essentially one exit point. If you're on the Rose-Hulman campus and you send a request that needs to leave, there is essentially one or a group of machines, probably a router, where that message goes to kind of at the edge of the Rose network that then goes out to the internet at large. And so that particular router, that access or that the gateway router, as we call it, where it's the gateway between your network and the rest of the world, that router is it's very important that it be done correctly and that it work very well, and that all the machines that are behind the network are able to share the resources, right? If every single computer on the Rose campus were to send a request for a message at exactly the same time, the router or set of routers that are in the Rose network would be so overloaded, most people would not get their responses back, at least at first. And so it's basically based on the fact that the probability of everybody using the network at the same time is really low. And so we need to switch between the different users, allowing each of them fair access to this gateway router throughout the rest of the world. And so there's different ways that we switch around which machine gets to have access to sending messages and all that kind of stuff, and when. And there's different ways to handle that. We have what's called a circuit switch, which is basically what the telephone system is based on, where it's like a physical connection, and each connection has a share of the whole bandwidth. This is how cable television works. This is how the telephone system works with circuit switching, which we're going to talk about before the end of this lecture, actually. So I'll say no more at this second. But then we have a packet switch network, which shares the medium in a completely different way than circuit switch. And we're going to talk about those here in just a minute. And so when we talk about messages being sent from one machine to another, the word packet is going to be used a lot, because in the internet, all messages are reduced to packets. And so a packet is just a portion of a message, right? If you're only needing to send a few bytes, then one packet is all you need, and you can send that packet. But if you have like a large file, that will be broken up into multiple packets that you can then send, piece by piece, and things like that. And so the last term here, store and forward, that is something we talk about when we talk about routers. And what that means is when a router is receiving a series of bits, it has to get the whole packet before it can forward it on, right? So it has to store the individual bits as it's getting them, because you get the message one bit at a time, albeit really fast, but you still only get it one bit at a time. So you need to store all those bits until you finally receive the full packet. And once you receive the full packet, now you can look in the information in what's called the header, which we'll talk about, where you learn where this message is destined, where it came from, all that kind of information. But the store and forward notion is that you have to get the whole packet before you can forward it. So you store it in RAM, and once you get the whole thing, you forward it on. Okay, so those are some terms. Here's some more. And some of these terms, like cloud, that is a really heavily weighted term. The term cloud has been used and misused for many, many years, and it's people are starting to kind of finally understand what a cloud means. But again, there are a lot of different ways that people define a cloud. But basically, for our purposes, you can just look at a cloud as a series of machines or servers that are interconnected that give you access to some kind of service. Whether it's, you're paying to use like Amazon's servers to host your website, right? That's a perfect use of a cloud. When Netflix first started, all of their infrastructure was through a cloud service, where Netflix did not have a single server that they could call their own when they first started. It's different now. But when they first started, basically they just rented other companies' cloud space and hosted their website and their video content in the cloud, which is just basically a set of machines that are connected that do different things as a service. We have software as a service, we have hardware as a service, we have platform as a service, and all those kinds of things. Okay, hosts is another term for node, but a host is specifically one that is more intelligent. It's running software of some sort. And then we have switches, which basically, whenever you have a network of more than one machine, in today's technology, they're connected through a series of switches, which could also be called routers. They're kind of sometimes used interchangeably. But essentially a switch is something that takes a message on one interface and figures out what interface that should go to. And let's see, so I'm just going to skip. So we have a router. That's basically a much more complicated switch. Routers are kind of things that give us, like, you have in your home probably a Wi-Fi router that gathers all of the different traffic from all of the machines in your home and forwards them out to the real world of, you know, the real internet. And so your gateway router at home is typically your Wi-Fi router. The last place that your network, like the outside edge of where your network connects to the rest of the world. And so, yeah, these other terms we'll see when we get to them. Okay, so, and this thing turned off automatically. Okay, so resource sharing and cost-effective resource sharing. This is a very, very important concept. And so this is a good picture to kind of show the issue, okay? So let's say over on this side, this is the Rose-Hulman network. And let's say on this side, this is the set of Google servers that respond to your Google queries, right? So we have one or a set of machines that switch the traffic or route the traffic or forward the traffic, as it were. And so it could be just one machine. It could be like at your home you have a single Wi-Fi router for all your machines, or you could, you know, talk more scale where it's the whole Rose-Hulman network, where eventually there is a router, or again a possible set of routers where all the traffic goes through. Whether it's going out or coming in, it goes through those particular machines. And that's where the cost-effective sharing of the resources is really important. And so, how can we effectively have many machines sharing the same switch, whether it's an actual switch or a router, which we're going to talk about the difference in those terminologies soon. But how do we effectively share? Well, this term of gathering all of the messages together to send them out onto the wire is the process, what we call multiplexing, okay? You're taking data from multiple sources, but they're all going out on the same link. And so you're multiplexing data. You know, you're gathering all the data and you're sending it out, right? But you hope that you do it in a fair way, where each of these have their own fair share of this link, right? This machine is what is standing between these machines and this link. And this link is really important. This is the link that connects you to the outside world. And so we want this switch to give a fair shot to all of the machines that are connected, so that they all get their fair share of this link. And so how do we share that link? There are many different ways. And so there are different forms of multiplexing, okay? And there is a type of multiplexing called synchronous time division multiplexing, STDM, okay? And so basically, time division multiplexing just says, okay, in kind of like a round-robin fashion, this switch is going to give a time slice to this machine, and this machine gets access to that link, like 100% access to that link, but this machine and this machine only for a certain amount of time. And then after that time slice is up, it moves to the next machine, and it gives that machine 100% access to that link. And then it keeps going, and it should do it in a fair manner where it gives each machine in the entire network a time slice, and then it starts over again. As you can imagine, the scalability of a time division multiplexing would be really weird if we had 1,000 machines on this side, but there was only, like right now at this instant, there's only one machine that's wanting to send stuff, right? We would want to make sure that if there was only one machine that wanted to send stuff, that it has much more access to this link, and we're still not like trying to give other machines a time slice when they don't want it. And so that turns out to be kind of a hard problem. So time division multiplexing works well when you're expecting all the machines in the network to constantly be sending and receiving data. But when you have sporadic, like moments of peak usage and then none, which is what most network access looks like, you request a page, that's a lot of messages, a lot of traffic, and then while the user is reading or watching a downloaded file, there's no more traffic on the network, and so it varies very much. And so we want a switch or a router that reacts to the traffic differently based on when it comes in. And so time division multiplexing is one solution, but it's not the solution. And then another way that we can break up this link is called frequency division multiplexing. And so whenever you have a link, okay, this link has, and we're going to use the term bandwidth here, but we're going to use it differently than the number of bits that you can put on the wire. Sometimes when we talk about bandwidth, we literally talk about the width or the number of frequencies that we can transmit on this link. Like, a copper cable might have, anywhere from 500 megahertz up to 2500 megahertz in terms of frequency. And that's actually how your cable television works. Whenever you're connected to the cable, the cable network, essentially when you switch channels, what you're doing is you are switching to a different frequency, and the channel that you're watching is broadcasting only on that one frequency, and so you're tuning in to that one frequency, and that's where how you get that particular data. And then when you switch channels, you then, so all the channels are basically being broadcast at the same time. You just pick one of those frequencies and you tune into that, and then you get the data only from that frequency. And so when we talk about doing that for machines with frequency division multiplexing, essentially that is where maybe this machine gets anywhere from 800 to 1,000 on the bandwidth, and this machine gets anywhere from 1,000 to 1,200, and so they can all literally transmit at exactly the same time, but because they're using different frequencies, it actually works out and there's no real main collision. Time division multiplexing basically gives you access to the whole bandwidth for a certain amount of time. Frequency division multiplexing gives you constant time access, so you always have access, but it's to a specific frequency. Now again, with frequency division multiplexing, if we only had one machine that wanted to send and it only had a small piece of the frequency or the bandwidth of that medium, if nobody else was sending, we would hope that you could get access to more frequencies so that you could send more data at once. But it's really hard to determine what machine we can give all of these frequencies to, because this instant maybe this is the only machine that's sending, but then the next instant maybe everybody wants to send something. So if they assume that they have access to that frequency, then you better make sure that they have it. And so whether it's time division or frequency division multiplexing, there are some advantages. Like, it really helps to make sure that each user gets a fair cut, but whenever you have one machine that's sending stuff and no other machines are sending stuff, the other machines don't need a fair cut of the network right now because they're just not using it. And so what we would like is a system that would react differently, where if only one machine were sending and receiving messages, it gets full access to this link. But as soon as we start getting multiple machines accessing the link at the same time, then we give it a fair break. a fair share. And so it turns out that when we talk about statistical multiplexing, that's where basically we give every machine full access to the link. But what you have to do is you break up your message into fixed size chunks, okay? And so this way, if you have a very large message to send, you break that message up into usually like 2,400 byte packets. And so you start sending your packets to that switch. And each machine can do this. And so the routers are designed to be able to take input from multiple interfaces at the same time, and then it stores those packets, figures out what link it needs to go out to, and then it sends those packets. So as long as every machine is breaking up all of its data into packets, as long as you're kind of taking the packets in a fair way, like, a round robin, where you take this packet and then this one and then this one, and then go back, take the next one and the next one and the next one, and so on and so forth, you see like the representation here that we have in memory for this switch. It has packets from multiple destinations. And so you start sending this packet out, and so the multiplexing is based on statistical use, right? If only one machine is sending packets, then the router doesn't need to do anything more than just take all the packets that it's receiving and immediately put them all on the link. And so that makes it look, if this machine is the only one sending or receiving messages, this machine then has the speed as though it has a direct connection to that link and no one else has it. But as soon as other people start sending, well, because they broke it up into packets, the more people have to send, they just keep sending those packets one by one, and the router in a fair fashion will make sure that all the packets that it receives, up to a certain point at least, it does its best, that is, to take all the packets and put them on this link in a fair way. And so you see that if everybody has something to send, different, like if you were to take a snapshot of the bits on the link, you would see packets from the different machines on the link at the same time. And so that turns out to be a much better type of multiplexing for the internet, because we have what's called bursty data. That's the term that we use. We say that network usage is very bursty in the sense that you want a web page, so you send a ton of messages, and there's a lot of data transfer back and forth. But as soon as it's done, basically that machine goes back to idle on the network, because the user is sitting there reading, and I mean, even 1 second is an eternity to a machine. It can do so many different things, and so data, by the very nature that it's coming from a human, it's very bursty. It's sudden, but then there's nothing. And so statistical multiplexing, breaking things into multiple packets, turns out it's not the slam dunk winner. Okay. It doesn't solve all of our problems. There are still problems that we have with packet switching, but it does kind of help scale in the sense, again, that if you have one machine sending, it looks like that machine has full access to the link. If you have multiple machines sending, as long as you treat those packets fairly, they all seem to have a share. And so your share grows and shrinks based on how many other machines are trying to use the link at the same time. And so when we talk about statistical multiplexing, we talk of flows. Okay, a flow of data. You can think of a flow as you were wanting to send this or request a file of this size. Okay, well, when you break that file or that request or that message or whatever into individual packets, all of the packets together constitute a flow of that data from one particular machine. So if you're sending a file, all of those packets that are a piece of that file are a part of the flow of data from that machine to its destination. And so a flow just kind of refers to multiple packets that belong to the same piece, if that makes sense. And so often packets and messages, the term is interchanged, but the thing is a full message might be too large and it must be broken into multiple packets. So when we talk about messages, sometimes we do mean the whole thing, the whole flow at once, but it may still need to be broken up into individual packets. Now, if your message is small enough, just like, a few bytes saying hello or something like that in text, then one packet is the whole message. And so that's kind of the difference there. And so there's different ways that you can statistically multiplex the data. You can do a first in, first out. Whoever is the first to start sending data is the first to get out. But that can kind of cause problems. And so round robin is just like take 1 or 5 packets from this, and then 1 to 5 from this, and then and you just kind of keep giving them each a fair share, and you kind of arrange the packets on the wire in a round robin way. There are also ways that you can define priorities. Like, let's say that, behind a Google network, this server is definitely got a higher priority than these guys because it's servicing some really, high dollar content or something like that. Well, you can give a priority such that, this flow of data should have more access to this link than the others based on a priority. And there's all sorts of ways to do this, but that's kind of the start of that discussion. And then when we talk about a congested network, what we mean is whenever so every router, every switch has a finite amount of memory. Now, memory is cheap, yes, and there is a lot of it, but as you know, especially with RAM, there is a limit to that. And so if every machine is just pelting this router or this switch with packet after packet after packet, eventually its memory is gonna fill up, and that actually can happen pretty easily. And so the question is, what happens whenever your memory is full and people are still sending you packets? So we want some means of having what's called congestion control, which means as soon as nodes start seeing that the network starts getting congested, you want to back off until the network can handle your data. So that actually comes along with TCP, as we'll learn. And so a congested network is just one that it's too many packets have been sent to a particular router, and it's not able to keep track. So what does a router do if its memory is full and it gets another packet? What would you imagine it should do? Well, it would be great if, say this guy sends a packet to this switch and the switch does not have any more memory. It would be nice for the router to send a message back saying, I don't have the space for that. But that's not how it works, because it would take more space to send that message back when you're trying to, send across the network. So it's not really feasible to tell machines that you're congested. So what do? Well, the current state of the art, the current protocol on IP says that as soon as a router's memory gets full, if it gets another packet, it just drops it. It doesn't tell anybody that it did. It doesn't tell anybody why. It just drops it. And then whenever you have a connection between two different machines, they can start determining if there are packets that have been lost, and lost packets gives us an indication that maybe something is being congested in the network or something's going wrong and we need to back off. And so we use that information to better transmit things. And then we talk about LANs and MANs and WANs. And so a LAN is a local area network. That's usually like a small Ethernet, like all of the machines in the same room. That's a local area network. Or, a local area network could be all of the machines behind the rows, inside of the Rose-Hulman network. Like that's a local area network where, in order to communicate from one machine to the other, you don't have to go through the internet at large. You just go through a few routers locally. And you have these server farms that are all connected, where you have servers on racks. A local area network could be considered one rack of servers. It could be considered all of the racks of servers in the entire building, and so on and so forth. But that's a local area network. And then we have metropolitan area networks. Don't talk about those too much. And then a wide area network. A wide area network is the internet, basically, where it's more than just, one network of machines. It's a network of networks. Okay. So when we talk about communicating messages and packets, sending back and forth with application to application, we want kind of the view that the application just kind of has a direct connection to the other host's application. And so we want to give these applications the view that they're just directly connected, as though one had a physical connection to a wire and the other had the other end of that wire. And so we have a logical connection, but it's really going through a bunch of routers, but we want to hide that fact. And so there are a couple of architectures or paradigms that we use to kind of define a generic protocol. And one of those is the oldest and probably most common, the client-server type of architecture. And this is the client-server communication pattern, as it were, is actually like pretty much all of HTTP, requesting web pages and things like that. You have a server that is holding the web page content, and then you have the clients that connect to that server, request a file or request a video or request a web page or whatever. And so the client-server model is a very generic type of protocol, but it applies to so much on the internet that we give it a name, the client-server model. The other extreme to that is the peer-to-peer model, where you have machines where there's no machine acting as a server, where it's only producing and sending content out based on request. You have a machine, a peer, that is downloading stuff, but it's also uploading to other peers. And so that's the other extreme to that. Basically, we're going to talk about both client-server protocols as well as peer-to-peer protocols. Okay, so we talked about the network edge, which is all of the machines on the outside, your servers, your computers, your phones, all of that. When we talk about the network core, that is basically a mesh of interconnected routers, okay? And a really big issue, a big question is, how does a router that gets a message from one interface, how, given this large collection of all of these networks, how does it know where this message should go, right? If this is a router on Rose-Hulman and you're wanting to send a message to a machine in China, then this router needs to somehow get the message to this router so that it can get to that machine. So how does this router know what link actually brings you one step closer to that router all the way on the other side of the world? Well, there are a lot of protocols in place that do this, and we will learn about how routers, the different routing algorithms, and then the process of forwarding is something else. So we talk about circuit switching. Remember, that's multiplexing. By the way, demultiplexing is just taking the data, like all the different data on the link, and figuring out what machine it should end up at. So multiplexing takes all the data and gathers it together to put on the link. Demultiplexing, on the other side, is getting all the data from that link and determining which machine it should then go to. And so circuit switching, where you literally have a physical connection where you're given a certain amount of time on that link or a certain amount of frequencies on that link, but it is a physical connection between you and that other host. And that's how the telephone network works. And so the internet was built on top of the phone network at first. And so that's why, circuit switching, so it's interesting because circuit switching kind of went away almost entirely, even in the telephone network, because it was just discovered that, we could packetize everything and, just use the network to send and receive only packets and not have any literal connections like the telephone networks used to. Well, it turns out that there are some advantages to circuit switching, and some companies are actually looking into doing circuit switching now, today, where, an ATM network, for instance, not ATM machine, an ATM network, which we'll see, that's a network protocol, that's actually kind of making a comeback for some applications, because there are some applications that absolutely need certain guarantees or it just won't work. And with a best effort service like the internet, you just don't get the guarantees that you need. And so circuit switching, the reason why we talk about it now is because it's starting to make a comeback. So you're going to need to understand what it means for a network to be circuit switched. And then packet switching, that's where everybody separates the data into discrete chunks, and you send those chunks out. And so we're going to look at both circuit switching and packet switching. So what I want to kind of end on for today is the concept of routing and the concept of forwarding. Okay, so every router has a set of interfaces. We call the links, the different physical linked connections, interfaces. So like take this router for instance. It has 4 total interfaces. It has this one and then these. And so you look at all of the connections to all these different routers, okay? They all have a certain number of interfaces that, this interface connects me to this router, and this interface connects me to this router. This interface connects me to this machine, and so on and so forth. And so the process of routing is determining what addresses are reachable through what interfaces. Okay, so there are a lot of algorithms that run. The process of routing is something that a bunch of routers run all at the same time to determine, okay, if you are in this range of IP addresses, all messages destined to this range of IP addresses goes this link. And then all messages that are destined to this block of IP addresses, they go on this link. And so this router determines the block of IP addresses that are reachable through interface 1. And then it determines all of the blocks of IP addresses that are reachable through link 2. Or interface 2, and then the same thing for 3, and the same thing for this other one. It just determines, if I get a message destined to a particular IP address, where does it need to go? And so it generalizes all of the IP addresses into like blocks with oh, the term is leaving me all of a sudden. Well, we'll get to it. You have packets that have an address to them, and you are trying to run a routing algorithm to determine if I get any packet from anywhere, if it's headed to this destination, I know what link to send it. And so the routing algorithm builds what's called a routing or a forwarding table, okay? And so this table is what is used in the forwarding process. So routing is the process of building this table on each router. So every router is going to have a table like this, and it says, okay, all blocks of addresses that look like this go on output link 3. All blocks of addresses like this and this go to link 2, and so on and so forth. And so we'll look at how those how that prefix matching works. once the table has been built, by the way, you periodically want to rerun the routing algorithm to update, because the networks are constantly changing, links are constantly going down, new ones are constantly coming up. You might change your direction to a particular machine based on traffic. It may be that for a particular IP address, it's reachable through 3, 2, and 1. You could send it on any link and it would eventually get there. That happens a lot. But which one is the most efficient? And so you look at which link, if I want to send to this IP address, which link will get it there the fastest? And so especially with that kind of information, you're going to want to change your forwarding table very rapidly. And so the process of when a router gets a single message, it's called forwarding. When it looks at its table and it says, okay, it's got this, so I match it to this address, okay, that means it needs to be sent on link 2. So the process of forwarding is when you take a packet from one interface and you determine through the table what interface it should go out to. Okay, and that's the process of forwarding. So routing and forwarding are two completely different things, but they work together to constitute what a router does. A router runs a routing algorithm to build the forwarding table, and then as soon as it receives a packet, the process of forwarding is looking up the packet's destination address, finding that, matching that destination address to one of my entries in the forwarding table, and then determining what link that packet should go out on, and then you put that packet on the link, and thus you have forwarded that packet. So as we go on in this class, when we say routing or forwarding, you need to make sure that you have some means of memorizing what it means when we say a routing algorithm versus a forwarding algorithm, for instance. Okay, so in terms of today, I think I went over just a little bit. My timer didn't start until I switched the first slide, so this is probably going to be closer to an hour-long video. Again, I apologize. But this is where we're going to stop for this particular lecture. We will pick up from here. We're going to talk about circuit switching and things like that, kind of in slightly more detail. And then after the next lecture, we will have another possible lab, depending on the material that we're able to cover. So thanks for sticking with me throughout this whole video. Hopefully this format is working for you. If you have any questions or whatever, please let me know. Otherwise, from the last video, you have Lab 0. Don't forget that Lab 0, you have a week to do it, and it's just a fairly simple 2 C programs, and we will get on to actual network programming in the very near future. So, that is all for this video.